Hello, this is my English speaking practice. I'm working on coding problems. Today's problem is majority element 2. Okay. Yep. Given an integer array of size n, find all elements that appear more than n divided by 3 times. And this notation means more than or equal to n divided by 3 times. Not equal to. For example, 1, 3, 2, 3. So n divided by 3 is 1. So we should find the element that appears more than this. So this means ceiling. This means ceiling. So in this case, n is 3, so this is 1, so more than 1. The numbers that appears more than once. So the answer is 3. This case, no one. I'm not sure this notation. I thought this is 1/3, so 0.333333. So this part would be 1, but it's not good. It's not correct. I think this part should be 0 in this case. So the answer is 1, just 1. So this notation means floor n divided by 3. I think so. So this case, n is 2, so this part would be 0.666, and this part would be 0. So 1 and 2 appears more than 0 times, so 1 and 2 is the answer. Okay, and yeah, this is my understanding and constraints. The length be 5 times 10 power 4, and number of values could be negative and very large range. And also there is a follow-up questions. Could you solve this problem in linear time and in constant space. Okay. Got it. So yeah. Let me some experiment. So there is a pattern regarding n. Oh yeah. So in this case, required to be more than one. So one is not enough, but this and this case requires to appear more than 0, so anything is okay. That's a pattern I get, and so yeah. So I think oh wait. Okay, I don't need to think about module, just find quotient. One, zero, zero. Yeah. Just find quotient. Yeah. How to count numbers in constant space? So I can find x. I can find x, and we have to find out numbers that appears more than x in linear time and in constant space. In this case, there is 10. There is 10 numbers, and 1, 2, and 3 appears 3 times, but 10 divided by 3 answer would be 3, so it requires to be 4 times. The element should appear 4 times. So I'm gonna find out numbers in the way to filter numbers rather than counting up. I think so. If x is 3, the number should appear 4 times. 4 times 4 times in 10 numbers. I have no idea. Filtering is difficult. Filtering numbers in constant space seems difficult, so I change my mind. Counting numbers in constant space. It's gonna use bit operations. Bit operations. Counting. Impossible. So let me see. This seems famous algorithm. For those who aren't familiar with Boiler-Moore majority vote algorithm, I found a great article that helps me to understand this fantastic algorithm. The essential concept is you keep a counter for the majority number x. If you find a number y that is not x, the concurrent counter should reduce 1. The reason is that if there is 5x and 4y, there would be 1 more x than y. This could be explained as 4x being paired out by 4y. And since the requirement is finding the majority for more than ceiling of n divided by 3, the answer will be less than or equal to two numbers. Oh, really? Exactly, makes sense. Okay. So we can modify the algorithm to maintain two counters from two majorities. Exactly. Yeah, so this is 1/3, so more than 1/3, so it will be less than or equal to two numbers. Yeah, that makes sense. So following more sample Python code, so we only have to prepare for two numbers. Two numbers would be the other candidates, and we have a counter for them. 0, 0, and 0, 1. Why this is 0, 1? And yeah, it's okay. Numbers, then if it's candidate 1, increment counter, and if it's candidate 2, increment the counter, and the L is not the candidate, and the counter 1 is 0, that is not candidate, so we can update the candidate 1 to N, and that count that the counter is 1, and for candidate 2 as well. Otherwise, I don't understand this. Okay. I haven't done algorithm post in a while, so the usual disclaimer first. If you don't find programming algorithm interesting, stop reading. This post is not for you. Program statement. Imagine that you have a non-sorted list of values. You want to know if there is a value that is present in the list for more than half of the elements in the list. If so, what is value? If not, you need to know that there is no majority element. You want to accomplish this as efficiently as possible. One common reason for this problem could be for Turing computing. You perform multiple redundant computations and then verify that a majority of the results agree. Simple solution: sort the list. If there is a majority value, it must not be the middle value. To confirm it's the majority, run the path through the list and count its frequency. This simple solution is O of n log n due to the sort, though. You can do better. Boyer-Moore algorithm. The Boyer-Moore algorithm is presented in this paper. The algorithm uses O of 1 extra space and O of n time. It requires exactly 2 passes over the input list. It's also quite simple to implement, though a little trick to understand how it works. In the first pass, we generate a single candidate value, which is the majority value if there is a majority. The second pass simply counts the frequency of the value to confirm. The first pass is the interesting part. In the first pass, we need two values, 1 First, a candidate value initially set to any value, a count initially set to 0 for each element in our input list. We first examine the count value. If the count is equal to 0, we set the candidate to the value as the current element next. First, compare the element's value to the current candidate value. If they are the same, we increment count by 1. If they are different, we decrement count by 1. And the end of all of the inputs, the candidate will be the majority value if a majority value exists. A second of n pass can verify that the candidate is a majority element. To see how this works, we only need to consider cases that contain a majority value. If the list doesn't contain a majority value, it is possible to trivially reject the candidate. First, consider a list where the first element is not the majority value. For example, this list is with majority value 0, 5, 5, 0, 0, 0, 5, 0, 0, 5. When processing the first element, we assign value of 5 to candidate and 1 to count. Since 5 is not the majority value, at some point in the list, our algorithm must find another value to pair with every 5 we've seen so far. Thus, at some point in the list, our algorithm must find another value to pair with every 5 we've seen so far. Thus, count will drop to 0 at some point before the last element in the list. In the above example, this occurs as the first element. Yeah, this part would be paired, so the list value and the count value. Yeah. At the point that the count returns to 0, we have consumed exactly the same number of 5s as the other elements. If all of the other elements were the majority element, as in this case, we consumed 2 majority elements and 2 non-majority elements. There is the largest number of majority elements we could have consumed, but even still, the majority element must still be a majority of the remainder of the input list. In our example, the remainder is 05005. If some of the other elements were not majority elements, for example, if the value was 4 instead, this would be even more true. We can see similarly that if the first element was a majority element and the count at some point drops to 0, then we can also see that the majority element is still the majority of the remainder of the input list, since again we have consumed an equal number of majority and let me read again. We can see similarly that if the first element was a majority element and count at some point drops to 0, then we can also see that the majority element is still the majority of the remainder of the input list, since again we have consumed an equal number of majority and makes sense. This in turn demonstrates that the range of elements from the time candidate is first assigned to when count drops to 0. And this in turn demonstrates that the range of elements from the time candidate is first assigned to when count drops to 0 can be discouraged from the input without affecting the final result of the first pass of the algorithm. This one mentioned that from to. Okay. The range of elements from the time candidate is first assigned to when count drops to 0 can be discarded from the input without affecting the final result of the first pass of the algorithm. Yeah, exactly. We can repeat this over and over again, discarding the range that prefix our input until we find a range that is a suffix of our input where count never drops to 0. Yep. Okay. Given input list suffix, given an input list suffix where count never drops to 0, we must have more values that equal the first element and value than given an input list suffix where count never drops 0, we must have more values that equal the first element than values that equal the first element and values than do not. Hence, the first element candidate must be the majority of that list and is the only possible candidate for the majority of the whole input list, though it is still possible there is no majority at all. Fewer comparisons. The above algorithm makes 2 passes through our list and so requires 2n comparisons in the worst case. It requires another n more if you consider the comparisons count to 0. There is another more complicated algorithm that operates using only 3n divided by 2 minus 2 comparisons, but requires an additional storage. The paper also proves that. Okay. But I'm not curious about this. Okay, but let me read. Their approach is to rearrange all of the elements so that no two adjacent elements have the same value and keep track of the leftovers in the bucket. In the first pass, you start with an empty rearranged list and an empty bracket. You take elements from your input and compare with the last element on the rearranged list. If they are equal, you place the element in the bracket. If they are not equal, you add the elements to the end of the list and then move on. Okay, I will parse. Distribute Boyer move. Of course, Gregable readers probably know that I like to see if these things can be solved in parallel on multiple processors. It turns out that someone has done all of the fun mathematical proof to show how to solve this in parallel. Their solution boils down to an observation with proof that first phase of Boyer movement can be うん。This algorithm can be multiple times where to combine parallel outputs in a tree-like fashion if necessary, or comparison. Okay, I almost understand, so let me code it. So in this case, more than 1/3 times, so we have two candidates. For example, n is 10, and divided by 3 is the quotient is 3, so so 4 times 4 times required, so we can understand there are two candidates at the most, so count 1 and count 2 and 0 0, and candidate 1 and candidate 2, anything is okay, but they should be different, so I set it 0 and 1. Yeah, and let's iterate over in over nums, and if count 1 is 0, we can set the candidate to n, because candidate 1, the current candidate 1 is not the actual candidate, so we can update. And otherwise, else if count 2 is 0, candidate 2 can be updated as well. And after that, candidate 1 and candidate 2 is the might be updated, so if candidate 1 equal to n, we count it up. Else if candidate 2 equal to n, count 2 should be updated, okay? Should be incremented by 1. And otherwise, n is not same both of candidate 1 and 2. Okay, in this case we should candidate 1 and candidate 2. Let me so in this case 1 and 2. And we have 3. Yeah, we have to find two majorities. Yeah, this case is I think let's go. So in this case, this part should be discarded, okay? Because equally appeared. So this part should be discarded, and this part should be discarded, and the last 3 gonna be the candidate. So I think this part should decrement both counter and yeah, and after the loop we have 2 candidates, so the answer would be answer would be 3 1 plus and 4 and enormous if n equal to candidate 1 or n equal to candidate 2. Oh wait. increment it, and more than x, append it. If count 2 is more than x, yeah, and return so. Yeah. Step 2, verify candidates. Okay, let me see the result. Oh, great. I think yep, if candidate 2 is counted. Might work. Oh, long answer. One, two, three, four, five, six, seven, 8. So x would be 2, and 1 is more than why? I think the one is I think candidate would be um, would be updated. 1, 2 is the first candidate, and we can count up 1. And when we get 3, this part should be discarded, but the 1 still remains. And 1 is still remains, and 4 is the second candidate at the time. But the 5 and 6 appears. I don't think. Why? Two and one, 2 and 1, 2 and 1, 2 and 1. 1 and 1. This is not good. 1 and 1. This is not good. I see. So we have 2 candidates, so I should if they are the same, it count up. They are not same. Oh wait. Not same means we can discard it, and if the counter I think if L is not the same, we have to check the count 1 at first, and if the count is 1, it's a timing when we can update the candidate. So yeah, we don't need to discard the counters, so the we update the counter, and count 1 should be incremented. Yeah, we have an opportunity to update the candidates, and otherwise, so it means n is not the same as candidates, and the counter is counters more than 0, so we have valid candidates, but the n is not if it's different from them, so we have to decrement the counters, I think. That's yes, that is algorithm. I think. One candidate 2. Let's go. Great. 0 1 2 1 2 1 2 1 2 1 2 1 4 1 4 1. Yeah. So 1 still remains. Makes sense. Let's go. Great work. So let me explain it again. So we have to find all elements that appear more than n divided by 3 times. That means, for example, n is 10, we can get a quotient of 3. It is 3, so more than 3 times. 4 times requires, it means more than 1/3. So we have 2 elements at most, right? Because more than 1/3, so there must be 2 elements at most. So we have to in order to find the answer in constant space, we just prepare two variables to store the candidates, and we also prepare the counter for them, right? So let me let's see the example. 1 1 2 3 4 1 2 3 1 2 3. This list, there is no answer because there is no element appears more than 3 times. In this case, the 3 is the answer because 3 appears 4 times. And the concept is like discarding the part, right? So this case, we can find the candidates. For example, 1 and 2 is the first candidate, and when we get the 3, all of elements appears once, so we can how to explain it? So we have two candidates. So yeah, we have two candidates. So for example, 1 and 2 is the first example, and when we get 3, it means 1 and 2 is not the candidate, because they have same appearance numbers, right? And when we get 4, when we get 4, this might be the candidate, because but it's not special candidate, because they are all appears once. Following my code, the candidate would be candidates never change until 3, and when we get 4, the counter should both counters should be 0. So the 4 is the candidate 1, right? And when we get 1 is the second candidate, right? And when we get 2, the counters should be decremented, so this part should be discarded, and we have two candidates, 3 and 1. And when we get 1, again, when we get 3, this part should be discarded, because they have same appearance. And when we get 3, 3 is the candidate 1. So so I think 1 and 3 remains as the candidates in this case. But at this time we cannot find out 1 and 3 is the answer, because this is just candidates, so we have to verify candidates. It should appears more than X. So we have we count the actual appearance at this part, and they appears more than X. We can append it to the answer, but 1 and 3 appears 3 times at most, so it doesn't meet the condition. So yeah, this function returns empty list. Otherwise no. On the other hand, let's see this example. This example 3 should be the answer, because they appears 4 times. But the algorithm is the same, so 1, 2, and 3, this part should be discarded. So when we get a 3, the code reach here, and count 1 and count 2 are decremented by 1, so counter returns to 0. Okay, so this part should be the same. This part should be the same, and we have 1 more 3, so 3 comes here, and 3 is not the candidate, because at this time candidate 1 is 1. Candidate 1 is 1. Oh wait, I'm not sure. 1, 2, 3. Yeah, 1, 2, 3. Yeah, 1, 2, 3. Yeah. I think, and they are remaining. They remains. So candidate 1 is 1. Candidate 2 is 2. And its counters is 0, and we have extra 3. So at the last time, counter 1 is 0 and candidate 1 will be overwritten to 3. Okay, so the final candidate should be 3 and 2, right? And verify candidates. Yeah, we can find out the valid candidate, and 3's counter should be 4. This is just counting the actual appearance, so the candidate 1 is the 3 and its counter should be 4, so the answer is 3, right? Yes. I think, yeah, that's good. Very cool. Okay, so let's go to the next. Lowest common ancestor of a binary tree. Given the binary tree, find the lowest common ancestor of 2 given nodes in the tree. According to the definition of LCA of Wikipedia, the lowest common ancestor is defined between 2 nodes P and Q are the lowest node in T that has both Q and P and Q as descendants, where we allow a node to be descendant of itself. Okay. So in this case, P is 5, Q is 1. 5 and 1. Must be 3. Okay. Because 3 is the only node that have 5 and 1 as descendants. Okay. And P is 5 and Q is 4. 5 and 4. Should be 5. Okay. The LCA of node 5 and 4 is 5, since a node can be a descendant of itself according to the LCA definitions. Okay. Yeah, I got it. So how to solve this? Basically, we can use tree work, and we have three kinds of tree work: pre-order, in-order, and post-order. But I think anything is okay. Anything works. Either works. So yeah, it's kind of DFS, and in the DFS, when we get P and Q, P or Q, yeah, it should return some flags. It represents there is a P or there is a Q, and yeah, and we have to find the lowest P and Q. Mm, yes, I think in order traversal should be the best. So DFS. Mm. Mm. I think we have four patterns. DFS function returns. So and so we have three three values, and for each we can get the information, and that challenge is to find out where is the lowest node, right? But this case, the DFS returns P and Q. The node must not be the answer because the left child have the lowest common ancestor, right? So as long as the DFS returns P and Q, the subtree contains P and Q, and the node itself must not be the lowest common ancestor. So yeah. And left returns P and right returns Q. The node should be the answer. The node is the lowest common ancestor. And node itself is P or Q, and the child returns P or Q. The node is also the lowest common ancestor. So we have so we just DFS and basically it in order. So the time complexity would be n, because there is n nodes, so and we visit each node at once, so time complexity will be O of n. Space complexity will be the number of call stacks, I think so. Call stacks would be depth of the tree at most. So let me code it. V is the node value. And this function doesn't return lowest common ancestor. This function just returns the information the tree contains P or Q. And by the way, this P and Q will exist in the tree. Okay, so there is the answer. There must be the answer. PQ. If DFS returns both, the function should find the answer, should find the lowest common node. So we can return yeah, it's almost done, so we return whatever, and otherwise wait, p node value equal p is q node value equal q. And p in L or R is p set to true. If not, is q, and q in L or R is q set to true, and if is p and is q, this node is the answer. So I think this this doesn't work. I think let me try. Return p return q return none, and return both. And DFS root return answer. Access local variable where it is not associated. All right. Yeah. The output is null. Really? Wait. 5 and 1. 5 and 1. P and Q. P and Q. Ah. Three returns both, but the answer is not updated, so I think yeah. How to this might work, but it's not cool, so this function should return the lowest common node between Q and P. So, for example, node itself and both. Return P, return Q. If L returns Can we compare them like this? Let me see. Oh, this works. So we can compare the node directory. So yeah, I think this works. Let's see the result. Okay, not bad. I'd like to see the complexity. What is it? Really? N is the number of nodes in the binary tree. H is the height of the binary tree. Yeah. Okay. My understanding is correct. Okay, so I got hungry, so I will finish. And today I'm going to participate in this weekly contest 474. Yeah, I have joined the contest 2 times before. I'm looking forward to it. Okay, so thank you for watching.